Welcome to the pre-recording of lecture 17, scheduled for 17th February. So this is our second lecture on GPU acceleration. And it's also in a sense self-contained. It's focused on the graphics hardware. And the key point here is the understanding. So the expectations of this part of the course, a course on supercomputing, is that you will get some understanding of why and how GPU acceleration works. So I'm following the textbook on the hands-on approach. So we will, next lecture, look into programming models. The second part of this lecture kind of explains the transition from graphics processing to programmable graphics processors and then to general purpose GPU computing. So I must admit that this is not my cup of tea hardware, and in a way it's kind of asymmetric with what we did earlier in the course. We did not spend quite some time on the internals of the CPU hardware, somehow because I was supposing that this is already well understood. But still, I think this lecture is important. If you understand the historical evolution, you will understand why the programming models are what they are. It's also, by the way, we will study pipelines as a tool to achieving parallelism, and the graphics processing is actually also a good example of a pipeline. The other textbook that we are following has one chapter on graphics processing towards the end as an application. Because of the importance of teraflop computing and actually personal supercomputing, the GPUs actually have taken now a more central stage, and I will repeat that in this course. GPU acceleration is the third pillar following message passing and multi-threading multitasking. So GPU acceleration is the third pillar for supercomputing. Okay, so there we go then. Here are the essential points. So we are doing massively parallel computing. So the way we are going to program GPUs seems very awkward at first, and understanding graphics processing will actually make that we will actually feel a little bit relieved compared to the technicalities that go into the graphics processing. So the key characteristics are massive parallelism, massive multi-threading as well. As we will see, we will need a multiple of the number of cores. The threads need to be a multiple of the number of cores. Memory hierarchies matter a lot. The increased memory bandwidth, which is now already expressed in terabytes per second at the high-end, most recent high-end current GPUs. So this is an advantage. But at the same time, as a programmer, we need to be extremely careful that we are not consuming too much memory. All right, so the purpose of this lecture is that the history will kind of provide the context for today and for the future evolution. So I grew up programming in the 80s, so I was past the punch cards, so I could type into a keyboard and see the results onto a screen. But these were shared mainframes and also workstations. So the evolution between the 1980s and the 90s was an enormous increase in performance, going from millions to billions of pixels per second. And also the number of vertices increased dramatically. So why was that? Well, because there is a very high demand for real-time graphics. So the architecture evolved from a very simple pipeline embedded into the hardware to programmable graphics processors. So the earliest GPUs were actually not at all programmable, and they were only offering a very simple pipeline. Now actually we will have several deep parallel pipelines. And the programmable graphics processor is kind of the intermediate stage between the earlier architectures and the current graphics processors that we can program with C++ and other languages. Okay, here is an image of the CPU versus the GPU. What is in between there is the PCIe, and that is actually something that I had to look up also. So the PCIe is the peripheral connect interface. So this is a standard for high speed connections, high speed memory connections. So between the CPU and the GPU. So the GPU has its internal memory, also the CPU has its memory. So when we implement, we have to be aware that everything that is on the GPU, everything that we want to accelerate has to come from the CPU onto the GPU, and everything that is computed by the GPU has to be transferred back to the CPU. There are integrated graphics cards, but one nevertheless in the programming models, one needs to be careful about these data transitions. So what else do you see in the CPU? So we have the memory, and on top of that we have the drivers and the interfaces on that the applications are using. The picture at the other side of the graphics processing unit has all the processors in the pipeline. So what is happening, and every processor in the pipeline actually retrieves, so at the beginning from the video memory, but then passes this through to the next processor in the stage, and there is reading and writing also to the memory of the graphics card. Okay, here is the now part for the graphics part. So every image actually consists of triangles. So there are application interfaces that allow for an application to send high-level commands to the GPU. And there is the interface to the GPU that is defined by the APIs. So there is OpenGL, where GL stands for the graphics language. Not to be confused with OpenCL, the command language. All right, so there are very deep pipelines. In the textbook, everything fitted on one page, but on the slides I had to separate it in several parts, in two parts here. So there is the connection between the host and the device. So the device, another name for the GPU. So there is the vertex control, the shading, the transform, and the lighting, which will define the setup of the triangles. And there is the main memory, but there is also the cache memory that stores the information of the vertices. So these are the three stages in the first part of the pipeline. So there is the image that is defined by triangles. So the corners of the triangles are called vertices. So the vertex data actually defines the triangles. Then one needs to define for every vertex what is the color. Then at a later stage, there will be the pixels inside and outside the triangle that will be colored as well. So a triangle is defined by corners and edges. So one have in the setup, one has the data that is associated with the edges. And also one needs to know which pixels are along the edges. All right, after the triangle setup, we have 4 more stages, the rastering, the shading, and the raster operations. And finally, it goes then into the frame buffer interface. There are more caches here for the textures and also for the buffers. So in some sense, there is the definition of the pipeline stages where all the operations that are happening, and in some sense you see also the caches that are already there. So the small memory locations. All right, so this picture illustrates a little bit the terminology. So we have the triangles, and the triangles are covering pixel areas. So one decides then what is the color of every pixel inside and outside the triangles. So the triangle geometry is what is explained at the left side. One has the aliased in the middle, and then there is the anti-aliasing. So I copied and pasted this picture from the second chapter from the handbook that we're following in this part of the course. So this kind of provides context. So this picture provides context for the operations in the second part of the pipeline. So what is rastering now? You have to decide which pixels are in or out every triangle. After the triangle setup, we figure out what are the edges. So one has to kind of combine the colors. One has the pixels that are kind of in between. And there is the anti-aliasing, which is then the third stage of the pipeline here. So at this point, everything is still on the GPU. It needs to get ready to get passed to the frame buffer interface to then actually go into the display. So, high bandwidth was one of the prime virtues and main advantages of using GPUs. So, how does one achieve high bandwidth? Well, for very special memory, and also by the simultaneously. So every portion of the picture can actually processed independently. So GPU acceleration is fine scheduled, fine-grained parallelism, and in a way, image processing, pixel by pixel coloring, is actually something that allows for a lot of parallelism. All right, that was the first part of this understanding. So we have the key notion of data independence. So I mentioned data parallelism in the first lecture, in the previous lecture, as one of the main prerequisites for GPU acceleration. So the stages in the pipeline, they do many floating point operations, but they do them on completely independent data. So almost pixel by pixel. And that is the prerequisite and also the characteristic of doing data parallel computing. It's also the most fundamental difference between the GPUs and the CPUs. So also the numbers here. So this is, keep again in mind, everything was designed for real-time graphics. So one needs to, in order to have somewhere a realistic game, or an enjoyable game, you don't want that things freeze somewhere in the middle while you're playing it. So everything must go very fast, so fractions of a second. Also a lot of data, millions and millions of triangles and pixels. So this is to indicate where the massive parallelism comes in. And also where the advantages come in from speed. Again, data independence is important. Okay, so the stages in the pipeline became also more and more complex. So here is one of the tasks that is done. The shading of the vertices. So we have the coordinates of the pixels. So here we have the shading and the shading program in the graphics pipeline. So the shader programs. So there is the red, green, blue model that is augmented by this alpha. The alpha determines how opaque every pixel is. So we go now into the intermediate stage of the GPU evolution, the programmable vertex processors. So the pipelines evolved from fixed instructions into the hardware by programs that were executed by the two stages in the shader, the vertex and the fragments. So one looks at the corners first, the corners of the triangles, and then one in the second stage one deals with the pixels that are inside, outside, or on the edge. And again, the main point that we hammer here is that all the data elements are independent from each other, are processed independent from each other, and therefore are quite naturally to run in parallel. So it looks, in a way, very sequential, but it is massively parallel if you think about millions and billions of pixels that are processed at fractions of seconds. Okay, so here is another picture. So we have two programmable processors. What is it actually that they are doing? We first deal with the vertices. So there is the inputs for all the vertices, the coordinates that come in, and what goes out are the red, green, and blue, and the opaqueness of every vertex. So that is essentially what the programmable vertex processor does in this first part of the pipeline. Now that is the pipeline which is done with GPUs, which are already more general purpose, not specifically baked in instructions, but that the graphics processor, the programmer who does the graphics processing, can program. I should say at this point in time that there are courses on graphics processing, programming graphics processing. I have no knowledge of that here, so that's why I'm still a little bit on shaky ground. But one can program the vertex processor and then also the second stage where one is going to deal with the pixels inside, outside, and on the edges of the triangles. That is then done by the second programmable processor, the fragment processor. We do tons of floating point operations. Speaking of floating point operations here, the RGB coordinates are typically 1 byte, encoded in 1 byte. So this also kind of indicates a little bit that the floating point operations can still be done by single float or even half floats. This is also one of the characteristics of the graphics processing, and also it explains a little bit the current trends in GPU computing to exploit more of the natural hardware by going to lower precision, if that can be afforded, to have more benefits. All right. So here is in words what I tried to explain why the pictures were shown. So for many complicated applications, the need for faster graphics, faster devices was coupled with also the need for more flexibility. So this is where the evolution of the programmability came in. So in a way, if the graphics application would still remain quite primitive, then we might never have gotten GPU acceleration because they would still be limited to very specific operations. But the fact that the vertex and the fragment processing operations became flexible enough, paved the way for more general floating point operations. All right. The evolutions were still such that this was still real-time graphics. So there is still a compromise here. So one always, whenever one gives more flexibility, it was still fitting within the requirements for having real-time graphics operations that could be executed in fractions of seconds. A limitation that actually was not really imposed on the central processing units. So one can kind of see that the power of the GPUs grow out of necessity, so to scale up, but in the same time with the real-time constraints of the graphics applications. All right, historically, so this is a historical evolution. So there is the GeForce 8800 GPU that was kind of the intermediate between the general purpose GPU. So the programmable processor became suitable for general numeric computing. So that meant that the graphics processing programmer naturally had everything in mind. Everything was a pixel, but one could start to think about the data as arrays of numbers. And that allowed for general numerical computing. As we will see in the next lectures, one of the staples in scientific computing is the matrix multiplication, and the GPU is extremely well suited for manipulating, for doing that type of operation. Here's some pictures. So this historical GPU was able to run in two modes. So it could run just as a graphics processor. So to do the vertex manipulations and the fragments of manipulations. So this is then the view, the graphics mode of this processor. So I took this from the slides from which this textbook is based. Then there is the other mode. So one can see this now as a more general processor where one has the thread execution manager. So that's actually the main point here, that one has the mode in which one can run the device with CUDA. CUDA stands for Compute Unified Device Architecture. When I first mentioned this last lecture, it sounded rather ambitious, kind of unified device, but here is where the origin of that word comes. So in a way, it is unifying both the graphics processor, so any graphics processor can still be used for its intended purpose of displaying images, high quality images, and it can also be used for general purpose numerical computing. So in a way, the word unified is hereby explained. So that is also a little bit the purpose of this lecture, to offer some understanding in the origin of the terminology. Okay, Good. GPU computing. So there is the GPGPU computing. So in the previous lecture, I was offering the quote that programmers experienced with MPI and OpenMP will find it not that hard to program GPUs. Well, in a way, this is a little bit it should be a little bit modulated. So if you, without the CUDA API, it would still be extremely hard because you would need to express your programs in vertex coordinates and graphics processing terms. So one would need to take a course in graphics processing before doing this GPU computing. There is the no double precision limitation. That's another problem. Although there is the float data type. So if you still have a GPU that is not capable of, that doesn't have a 64-bit floating point processors, then you can still work with the float type. So at the time when the first edition of the textbook appeared, this was 2010, so most likely the next generation that was shortly before 2010 was called Fermi. So you see that then already there were 64-bit floating double precision floating point processors. A lot of accommodations and adjustments that were made for scientific computing. So again, explaining a little bit the unified nature of this device architecture. Which, so C stands for compute, but C also stands for the C programming language, which also then means that C is a general purpose language. Sometimes people refer to C as a language of the past. More and more I'd like to see C a little bit as the least common multiple, but more the greatest common divisor. If you understand C, then you understand actually a lot of ways to program. So in this course we will see many others. So I've been advocating and using Julia and in addition to Python, but knowing C is still an encouragement here. Okay, so I'm halfway, more than half an hour into this lecture. We will look at some pictures now. So here is a schematic. So in the last lecture, I was indicating that in contrast to the CPU, the cores in GPU are much more limited. Here you have every core that has two type of units. So there is a floating point unit and an integer unit. In some sense, this is probably an oversimplification. You may have cores, floating point cores that can do 32-bit and that can do 64-bit in one core. You have the controllers and the caches. So in some sense, every core has space for registers. And that's important to know. And every group of cores, we call that a warp, they have their device memory, which could be considered as some type of cache. So this picture should probably have started with that as well. So the big block is one streaming multiprocessor. So one streaming multiprocessor is capable of steering one particular type of instructions. So the streaming multiprocessor is a little bit more analogous to the processor on a general CPU. So you have a multi-core GPU. So one streaming multiprocessor would more correspond to a general arithmetic and logical unit on a CPU. So that's kind of the analogy a little bit. All right, so we are using Pascal in this course. So here is a picture from the white paper. So in this lecture, I try to give a summary, an overview of the material that is out there. There are no specific exercises except that for you to go looking into these white papers. They are publicly available from the NVIDIA website. This is a picture I took from it. So this again is a very good picture of the streaming multiprocessor. And you can also see the parallelism that is in there. So every streaming multiprocessor is capable of scheduling 2 lanes of instructions. So you can see that there are 2 instruction buffers there. And there is a warp scheduler. So if one streaming multiprocessor has 64 cores, then they're actually divided up in groups of 32. And as I'm rambling here, so you can see the green blocks labeled core. In total, there are indeed 16 plus 16, that's 32 in one at the left, and then at the right, you have also 32. So you also see the registers that can be used. So later when we will do some programming, it's important that as a programmer, use registers. Certainly this is for fast memory, but don't use too many because that will prevent the scheduling of the instructions. We will get back to that later. So there were 2 instruction buffers in one streaming multiprocessor. So here you see the warp scheduler. So, and this indicates a little bit the single instruction on multiple data. So there is this data independence. We have 32 threads which execute the same instruction. And in order for the parallelism, in order for the GPU to become fully occupied, one must have sufficiently many instructions scheduled, because sometimes one instruction is prevented from execution because it's waiting for data. So here you see one schematic of the scheduling that is happening. All right, so the G80 was mentioned as the kind of the intermediate, the first general purpose GPU which could run in graphics mode or as a CUDA device. You can see the number of transistors. So the Fermi architecture was at the end towards 2010. The G80 was in the middle of the first decade of this century. So you kind of see the evolution. More transistors and also more cores and running faster. So the G80 still had no double precision capabilities, but then the later editions actually did. So that made them quite suitable for scientific computing. So currently per streaming multiprocessor there are 2 warp schedulers. That means that if you have 64 cores per streaming multiprocessor, because there are 2 for one streaming multiprocessor, this implies that you can often get good performance by scheduling already with 32 blocks of threads organized in groups of 32. Not necessarily has to be 64. Okay, then going further, so Kepler was the first card that had a theoretical peak performance of teraflop. So you can see the specifications. The limitations of the memory. So we had more and more cores, but actually the memory did actually not grow that much. So it's probably one needs to look at the shared memory size. So it kind of stayed a little bit 16 kilobytes. So this still refers to the small caches that I mentioned earlier. If you are programming on a machine like Pascal that has 256 gigabytes of internal memory, then you should not be too concerned that somehow your multiprocessing program consumes too much memory. If you do a massive parallel processing, you have to limit the amount of memory that each thread can use. Also the number of registers per thread. So going from Fermi to Kepler, you can see that the number of registers per thread was still limited. There is the compute capability. I will indicate in a future lecture what that actually really means. So there is going from Kepler to Pascal. The number of threads, so what has been constant throughout, that is the number of threads in a warp. Again, that warp size is kind of the minimum you have to think about when you, the minimum units of instructions, so you should think in groups of 32. Although with compute capability 6, atomic operations were supported by the hardware. So there are the memory hierarchies, which also exist in the CPU. So this is what I mentioned earlier on, the asymmetry. So also when one really wants to do high performance multiprocessing, multitasking, one needs to also be very well aware of the cache sizes, the number of registers, and the movements between those. And we will see later on applications that indeed are fine-tuned for this. So here is the memory hierarchy. Every thread has shared memory, but then there is also the cache. And there are read-only memories, which are very good for storing constants, global constants that every thread would need to know. Okay, I managed to get through this lecture without too many hiccups. So this is not my cup of tea, this hardware. I have never taken and never done any proper graphics processing. But nevertheless, I hope to have brought some understanding. So we are with the instruction level parallelism, to fully occupy the GPU, one must schedule in a way that you are using a number of threads that is a multiple of the number of cores. If you would have that thinking with multi-threading and multiprocessing, that would be extremely bad. With multitasking, we have seen that we can generate exponential number of tasks and still not swamp the CPU. So in some sense, within our experience from multitasking, it's not that bad. What is the key difference is the data independence. So fortunately, many scientific applications, and perhaps even almost all scientific applications, involve linear algebra. And these linear algebra operations actually can be accomplished in a data parallel view. Okay, so more references. So there are no specific exercises other than, again, look up the documentation for the graphics cards that is in your laptop, in your personal computer. If it is an NVIDIA one, then you can do already, you can follow quite along with the CUDA model. If not, there are general purpose tools available that will allow you to program your GPU. So in a way, that's actually kind of the main point again, why this is still one of the fundamental pillars of computing. Um, Graphics processing units are everywhere. You typically always, when you buy a computer, you have a monitor there, you have a graphics card, and often we have the specification of the CPU. How fast is your processor? How fast is your memory? But then also, how strong is your graphics card? So these are the three main characteristics corresponding to the three pillars of computing, more or less what we see in this course. So I hope that this lecture was insightful, that it will provide some background for the next lectures where we will look into programming models and into some key applications for scientific computing.